So Bismillah ar-Rahman ar-Rahim. Continue with the digital audio sound. So it's a second part of digital audio sound. So as we studied about sampling, so now we are going to be study about quantization. So in the sampling we saw that how we can sample the analog signal, and so and how much we can get the sampling rate from the sampling. So now we are going to be study about quantization. So in a quantization, what does it mean? So if you remember, each of the discrete samples of amplitude, like if you can see this all is amplitude, this one, this is all amplitude. Keep in mind, this is all amplitude. What we are going to do, that if this value is roundabout, let's say this value is 1.2, let's say this is 1.2. so what we can do, we are going to make this value to be round off. We can be said it can be 1.5, or we can say it can be 1. We make it round. So in a quantization, that's a basic method how we can quantize. So each of a discrete sample of amplitude values obtained from the sampling steps are mapped and rounded to the nearest value on a scale of a discrete level. Okay, so now the number of a level in the scale is expressed in a bit depth. So keep in mind, what is bit depth? Which is related to the number of a level, and number of level, you know that it's all about power of a 2, mean 2 raised to power n. So in a third way, an 8-bit audio allows 2 raised to power 8. So, you know about 2 raised to power n, so bit is 8, so 2 raised to power 8, which is 256 possible level in the scale. And the CD quality audio is 16-bit, which is possible 65,536 possible level. So keep in mind, what is quantization? Quantization just rounding the amplitude value to the nearest figure. So suppose we are quantizing the sample using 3-bit. 3-bit means 2 raised to power 3 is 8 level. So how many level you are going to make? 1, 2, 3, 4, 5, 6, 7, 8. So how many level we have? 8 level. So what we are going to do? We are going to be convert this analog signal with the help of 8 level and with the help of a 3-bit. So this is level 1, like going to be C, where we have a amplitude figure. So this is the amplitude which is already be round off. It's not a round off, we need to be round off. It can be upward. Okay, so it may be near to this one, it can be round off with this one, it near to be this one. Now round off with this one, round off with this one. So what we can do, we just round off. Let's see, this value is 1.8 and this is near to be 2, so we can say it's 2, and this is round about 1.9, so we can say it's equal to 2. This is called quantization. To make an amplitude value to be a round off. Round off means 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.55, and so on. Okay, so this is the way how we can make a quantization. So now if we can see round each sample to the nearest value. So this already be round off with this one, and this is round off with this one, round off with this one, round off with this one. It already be rounded, it round out with this one. So this is the image. Once we are going to be round off the amplitude value with the nearest whole number value. Okay, so this is the method. If you can see the dotted line with the black, which is the original one, and the orange dot is like a round off figure. So now what we can do, we are going to reconstruct the waveform using quantized. Now those values, those quantized amplitude values, which we quantize it from the old value, then now we can make a waveform from that. So that was our quantized one. So make it with the waveform with this one. Okay, so now our signal will be in this shape. So now coming to the effect of quantization. So our data with a different original amplitude may be quantized onto the same level. So you already cite in the graph as well. So loss of subtle differences of a sample, you can below sum of it, you can be near to be a 0. With the lower bit depth, with the lower bit depth mean the level is going to be lower, number of level is going to be lower. So sample with a larger difference may also be quantized onto the same. It is about the effect of quantization. So now this is a concept of a bit depth, which is most important to be understand, because always we guys are looking in a market that we need to find a good quality of audios. So for a good quality of audio, we need to be think about the bit depth. So bit depth of the digital audio is also referred to as resolution. Resolution of a audio signal or digital audio signal is based on a bit depth. For a digital audio, higher resolution mean higher bit depth. Okay, so you hope you guys understood that, because from last 4 to 5 lecture we are talking about number of level, number of bit, number of level, and number of bit. Increasing a level, increasing the bit, brightness, quality, image, graphic, all these things, and the resolution, all these things is depend on the number of a bit and the number of a level. So now coming to a dynamic range, again the same as we cited in the previous example, the range of the scale from the lowest to the highest possible quantization value, as we cite in the. So in the previous example like this one, we have a lower value and we are going to be round off with the higher value. So this is called dynamic range of a quantization value. So what is the basically effect of a bit depth? So the choices of a sampling rate and a bit depth, higher sampling rate and a bit depth, so deliver better fidelity of a digitized file. So for a better fidelity, you want to show your fidelity, you want to show the fidelity of your quality to the customer. So what you will do to increase the sampling rate with the bit depth. And the second is when the bit depth is going to be increased, so the result in a larger file size. Okay, file size is going to be increased. So now coming to the numerical problem, estimating 1 minute CD quality audio, 1 minute, and we always be calculating the sampling rate, bit rate, whatever in a second, but it's a minute. So 1 minute is equal to 60 seconds. Keep in mind. Okay, coming to what is our sampling? Our sampling rate is 44,100 hertz is our sampling rate. Okay, then so it means so 44,100 hertz in a 1 second. So for example, it should be a 44,100 sample per second. So what is our bit depth? Bit depth is 16. So it means how many bits will be in a 1 sample. So 16 bit per sample, because our bit depth is 16. So 16 bit per sample. And so what kind of a channel we are going to use? So we are going to use a stereo channel, because it's a audio sound, it's a range of, it's a quality of a audio. So using a stereo, which is 2 channel, left and right channel. Okay, so now coming to the 1 minute, which is equal to 60 seconds, our sampling rate was 44,100 sample per second. So it will be multiplied with 60 seconds, because in a 1 minute we have a 60 seconds. So multiply with the 60, it will be 264,600 samples. Okay, second with the second will be cancelled out and we will get as samples. So this is simple. So now total number of a bit required for these many samples. Okay, so we know about bit depth was 16 bit per sample. So for 16 bit per sample need to be find out the total number of a bit from a samples. Total number of bit from this one, what we can do, 16 bit per sample multiply with it, simply cancel out. It's our, this is for one channel. For one channel we have this number of a bit. So for two channel multiply with the 2, so 42,336 bit per channel multiply with the 2 channel. Okay, so channel cancel out, to multiply with this one. So the total number of a bit is the channel or stereo channel is going to be used, which is equal to 84,672,000 bits. So this is the way how you guys can calculate it in a term of a bit. If somebody can ask, they find out number of a sample, so do it for up to this extent. If somebody asked it find out the bit for one channel, do it on this point. Somebody asked that for a two channel, do it on this point. So find out the file size of a 1 minute CD quality audio. So we have a number of bits. Okay, so number of bit 84,672,000, this one. Okay, so we are going to take a byte, and you know about a byte, which is 8 bits. Okay, so multiply, divide 84 with the byte, because you are just converting the bit into byte. So just the simple thing is divide by 8, because 1 byte is equal to 8 bit. So which is divided and we get 10,584,000 bytes. Okay, then we are going to convert this whole value into kilobyte. In the value of kilobyte, in the kilobyte you know about 10242 raised to power 10, I think so. It's so it's equal to be 1024, which is equal to, like, this number is going to be convert divided by this one, the number is going to convert 10,336 kilobyte. Okay, we always we take a and the value of a size in a kilo or a mega or a gigabyte. So now this is our kilobyte, so we need to be change kilobyte to megabyte. Okay, again going to be converted again, the 1 megabyte is equal to 1024 kilobyte divided, so the result will be near equal to 10 MB. So now because you are going to be see the size of the file, so you see how many MB it will be. So now this file is going to be a 10 MB, where you have a 16 bit per sample, your sampling rate and so on. So this calculation as we did, this is for a 10 MB file. So now coming to the general strategies to reduce a digital media files. If you want to reduce the file of the size, so what you can do, reduce the sampling rate, reduce the bit depth, apply compression. I told you before as well, sampling rate, bit depth, and the third one is compression. For a digital audio, these can also be option, reducing the number of a channel, you can be do it, shorten the length of the audio, you can be do it. Okay, so these are the some specific method how you can be reduce the size of the file. So now coming to the reducing a sampling rate, again it's all about reducing the file size. So once you are going to sacrifice the fidelity of your digital signal, so you can be reduce the sampling. When you are going to reduce your sampling rate, so your quality is going to be a little bit going to be a buffer, like disturb, not going to be a bit in a good quality. So once you are doing that, it means you are sacrificing your fidelity. The second is need to weight the quality against the file size. It's again the based on reducing a sampling rate. So the third is need to be considered human perception of audio. For example, how perceptible is the audio with the lower sampling rate. and how the audio is used. So the music can be managed higher sampling rate, short sound clips such as explosion and looping, ambient background, noisy may work well. So it's all about the sampling rate. So it's up to you. Once you want a good signal, once you want a good quality, increase your sampling. If you want not in a medium one, so reduce your sampling and so on. So all about your sampling rate, bit rate, sampling rate, channel, and so on. And so you guys also know about the human hearing range, which is 20 Hz to 20 kilohertz, most sensitive to be 2 kilohertz to 5 kilohertz. It's more sensitive. So coming to some theorems, which is you already studied it in data communication about a channel. We have two different channel, noisy channel and noiseless channel. So for noisy and noiseless, we have two concepts, Nyquist Theorem and channel. So the Nyquist Theorem is we must sample at least 2 points in each sound wave cycle to be able to reconstruct a sound wave satisfactory. So sampling rate of the audio, which is always greater or equal to the twice of the audio frequency. This is called Nyquist. It's like this one. If you can remember, your sampling rate is always greater or equal to the twice of the audio signal. Okay, this is your sampling frequency, this is your original one. So this is Nyquist theorem. So sampling rate of the audio is higher for a audio with the higher pitch, because when pitch is going to happen, the frequency is going to be high. So this is about the Nyquist theorem. So the most common choices of a bit depth, which is you can be 8-bit. 8-bit is usually sufficient for a speech, in general too low for a music. 16-bit is minimal bit depth for a music, and 24, 32-bit is can be. So this is the most common choices using for a bit depth. So then coming to the audio file compression, when we have an audio file, in audio file we have some lossless and lossy thing. So like just like a get rid of some data, but human perception is taken into consideration, so that the data removed causes the least noticeable distortion. So it's just about compression, and like MP3 is a good example for that. So the basic thing, as we studied about digital audio, so we have a signal in an analog form, and we are going to be change the analog into digital using a sampling and quantization, and we can also say that we have PCM, pulse code modulation, or analog to digital conversion as well in data communication. So as we say, calculate some of the example as well. So it was a method how we can calculate and how we can convert the analog to the digital audio quality. So we have some extra slide here, which is about common audio file, wave, MP3, M4A. So it is just like for your information, just go through it and read it. It will help you. Then again, common audio file type and so on. And then at the end, choosing an audio file type, it's up to determined by the intended use, like file size limitation, intended audience, whether it is a source file, is your audio used on a web, file type, date, offer high compression, streaming audio file, etc., etc. So again, it's all about your audience now. So hope this lecture will help you in your future as well. So you guys watch it out. If you have any questions, so mention it on a comment, so I will try to solve it and will share with you. Thank you for your time. See you in the next lecture.